At the top of the world, in a place so cold your breath freezes mid-air, there is an animal with a problem you would not expect. It is not freezing, it is overheating. The most extreme predator of the Arctic is in danger of cooking inside its own fur coat, in a world that is getting warmer every year. So how do polar bears survive in a melting world, when the very ice they stand on is disappearing beneath their feet? Because to understand that, we have to start with the battlefield itself, sea ice. For a polar bear, sea ice is not just scenery. It is a hunting platform, a highway, a nursery, and a shield. They are classified as marine mammals because they depend on ocean ice to reach their food. According to the U.S. Geological Survey and the National Snow and Ice Data Center, Arctic sea ice is shrinking in both area and thickness, with September sea ice extent declining by about 12 to 13% per decade since 1979, relative to the 1981 to 2010 average based on satellite records from NASA and NSIDC. That means every decade, the summer hunting ground of the polar bear is losing more than a tenth of its reach. Less ice does not just mean less space. It changes where seals surface to breathe, how predictable breathing holes are, and how far bears have to swim to find the next flow. It stretches the distance between food and safety like a rubber band. But the real twist is this. The same design that made polar bears rulers of the frozen ocean also traps them when that ocean begins to thaw. Look closely at a polar bear and you see white. But under that dense white fur is skin as black as coal. Under the skin, a thick layer of fat that can reach more than 10 centimeters on a well-fed adult. Documented in field measurements by the U.S. Fish and Wildlife Service and the Norwegian Polar Institute. The fur itself is not just one coat. There is a woolly underfur for insulation and longer guard hairs that repel water and snow. Those hairs scatter and reflect visible light, which is why the bear looks white, but the dark skin underneath is extremely good at absorbing sunlight and turning it into heat. This combination keeps the bear so warm that in air temperatures as low as minus 30 degrees Celsius, a resting, well-insulated adult loses almost no measurable heat, as shown in thermal imaging studies published in the Journal of Comparative Physiology. In fact, researchers at the University of Oslo found that polar bears are so well insulated that they risk hyperthermia when they run for more than a couple of minutes above freezing temperatures. But the thing that really keeps them alive out on broken ice is not what you see on top. It is what is hidden in that thick, greasy layer underneath. Their blubber is a bank account of calories, storing energy from seal fat in dense, slow-burning form that can keep a fasting bear alive for months. The price of this armor is that every kilogram of insulation makes movement more expensive. So how does an animal that overheats easily and carries a huge coat of fat manage to hunt in a world where the ice is vanishing and the water gaps are getting wider? Start with the feet. A polar bear's paws can be up to 30 centimeters wide in large males, roughly the size of a dinner plate, according to measurements recorded by the Canadian Wildlife Service. These paws spread the bear's weight like snowshoes, reducing the pressure on thin ice. The soles are covered in tiny papillae, rough bumps that increase friction on slippery surfaces, and tufts of fur that add grip while providing insulation. The claws are sharply curved ice hooks that can grip the edge of a floe or slash through seal flesh. Inside the body, a powerful circulatory trick called countercurrent heat exchange helps the bear balance heat and cold. Arteries carrying warm blood from the core run close to veins, bringing cold blood back from the limbs. Heat transfers from the outgoing to the incoming blood, so by the time blood reaches the paws, it is cooler, and by the time it returns to the heart, it has been pre-warmed. This reduces heat loss into ice and snow and prevents the animal from wasting energy just to keep its extremities from freezing. Similar systems exist in Arctic foxes and reindeer, but in polar bears it is pushed to an extreme. Yet as temperatures rise and sea ice seasons shorten, this fine-tuned balance has to work harder. The same mechanisms designed to prevent freezing now have to dump excess heat from a body built for -40 into an environment that is increasingly sitting at 0 or above. Their own perfection becomes a limitation. To eat, a polar bear needs seals, mostly ringed and bearded seals. But seals are fast and spend most of their time underwater. On open water, a bear is out of its element, so it turns the ice into a trap. Across the sea ice, seals maintain breathing holes to access air. Bears learn these patterns. They know where the smells concentrate, where the wind carries the trace of seal breath. In controlled tests, scientists from the University of Alberta and Environment and Climate Change Canada have found that polar bears can detect seal-related scents from over a kilometer away, and possibly farther depending on wind conditions. Their nasal cavity is large and complex, packed with folded turbinate bones that create a huge surface area for scent receptors, allowing them to filter and decode faint chemical signals in the cold air. The classic hunt is a stakeout. A bear finds an active breathing hole, uses the wind to stay downwind, and waits, sometimes for hours, motionless. It balances on the edges of the hole, claws ready, nose reading the air. When the seal surfaces, the bear's reaction has to be instant. One explosive strike with a forepaw, one bite to the head. If it misses, the seal is gone. That level of patience is not optional. It is an energy calculation. Polar bears have among the lowest field metabolic rates for their size of any mammalian predator, based on data collected with GPS and accelerometer collars and published in the journal Science in 2018 by Pagano and colleagues. But even so, every wasted chase burns precious fat. That is why you so rarely see a polar bear sprinting across the ice. It is not laziness. It is economics. Yet the real secret weapon in their hunting playbook is something you cannot see at all. The key is how they manage time itself. In a stable Arctic, bears synchronize their most active, energy-expensive hunting with the period of maximum sea ice coverage in late winter and spring, when seal pups are abundant in snow dens and adults haul out more often. They binge. Then, as summer comes and ice recedes, they hit pause. Many populations, especially in Hudson Bay and parts of Canada, are forced onto land for ice-free months. Here is the twist. Polar bears are not hibernators in the classic sense. Only pregnant females enter a hibernation-like state in maternity dens. Adult males and non-pregnant females stay technically awake, but they can depress their metabolism and reduce movement dramatically. Studies using doubly labeled water and satellite tags, like those by Sterling and de Rocher and later by Rode and colleagues, suggest that during prolonged food shortage, bears can lower their metabolic rate by roughly 20 to 25% compared to active hunting periods, though there is debate about the exact magnitude and mechanisms. They also rely on that thick blubber. A large adult with a fat reserve built up in spring can survive several months with little or no food, losing weight but staying alive. The limit, however, is strict. Research published in Global Change Biology and other journals estimates that in some subpopulations, like western Hudson Bay, bears are already approaching the maximum fasting period they can survive, which modeling suggests is on the order of 180 to 200 days for many individuals, depending on starting body condition. As ice-free seasons lengthen, that fasting runway shrinks. There is only so much fat you can carry and still move. So scientists have started asking a painful question. What happens when even the best-built fasting machine runs out of time between meals? Reproduction is where timing becomes everything. In autumn, after mating in spring, fertilized polar bear embryos actually pause their development in a process called delayed implantation. Only if the female has built up enough fat will the embryos implant and start growing. This strategy, documented in comparative carnivore studies from the University of Saskatchewan and others, lets the mother's body decide whether she can afford to be pregnant that year. In late autumn, a pregnant female digs a den in a snowbank, or in some regions, on stable land or drifted pressure ridges on sea ice. Inside this cramped, airless cave, temperatures may stay just below freezing, even when the outside air howls at -30 or -40. She gives birth to tiny cubs weighing around 600 to 700 grams each, according to the IUCN Polar Bear Specialist Group, blind, nearly hairless, completely dependent. For months, she does not leave. She does not eat or drink. She lives entirely off her fat, converting it into extraordinarily rich milk that can be more than 30% fat. When she finally breaks out of the den in late winter, each cub may weigh 10 to 15 kilograms if all has gone well. But this entire system depends on having deep, stable snow and predictable ice conditions. Observations from Svalbard, the Barents Sea, and parts of the Canadian archipelago, published in journals like Arctic and Polar Biology, report more frequent den collapses, earlier rain on snow events that harden or melt den roofs, and shifts in where females choose to den as sea ice becomes less reliable. Some bears are forced to den on land farther from good spring hunting areas. Others may have to walk or swim longer distances with small cubs to reach the ice. Cub survival is highly sensitive to the condition of the mother. If shortened hunting seasons leave females leaner before denning, more embryos fail to implant. More cubs are born small, and more die in their first year. The bears are not just losing ice. They are losing the quiet, predictable winter room where new life begins. In this changing Arctic, the phrase "built to survive" starts to sound risky. Polar bears are superbly adapted, but those adaptations are tuned to a world of thick, multi-year ice and short summers. In some regions, scientists have documented behavioral changes. Bears in western Hudson Bay are eating more bird eggs and vegetation while on land. Individuals on Svalbard have been seen scavenging whale carcasses or raiding human garbage more often. A few studies, including ones from the Norwegian Polar Institute and the University of Washington, suggest that in certain years, bears may partially compensate for shorter ice seasons by moving farther or switching prey. But the consensus from long-term monitoring, like the 2023 assessment by the IUCN Polar Bear Specialist Group, is that most of the 19 recognized subpopulations are either stable with warning signs, declining, or data deficient, with the best documented declines in places where sea ice loss has been fastest, such as western and southern Hudson Bay and the southern Beaufort Sea. Estimates published in Nature, Climate Change, and other journals project that if greenhouse gas emissions continue on high trajectories, many polar bear subpopulations could experience severe declines by the end of this century. There is debate around the exact timing and magnitude, and some researchers argue certain high Arctic regions with more persistent ice, like parts of the Canadian Arctic archipelago, may act as refuges. But even the more optimistic scenarios rely on emissions stabilizing and warming slowing significantly. The uncomfortable truth is that no amount of perfect fur, perfect paws, or perfect hunting strategy can fully offset a habitat that is vanishing faster than evolution can respond. So where exactly is the edge? Not the edge of the ice, but the edge of what a polar bear can endure. Physiologists talk about thermal neutral zones, the range of temperatures in which an animal does not have to spend extra energy to stay warm or cool. For polar bears, that zone is far below what most humans would tolerate. Behavioral ecologists talk about energy landscapes, the balance between calories spent and calories earned as an animal moves through its environment. For polar bears, that landscape is steepening. Swimming long distances between flows has a high energetic cost. A 2011 study in polar biology by Pagano and others found that adult female polar bears swimming more than 50 kilometers were at risk of losing cubs and burning significant fat reserves, especially when forced to repeat these long swims. Each additional week without ice in late summer pushes that cost curve higher. There are still uncertainties. Some populations, like those in parts of the Chukchi Sea, have remained relatively stable in body condition as of recent surveys, possibly because local productivity and prey availability are still high even as ice patterns shift. Other regions show sharper declines. Scientists debate the capacity of bears to find new foraging strategies, to exploit terrestrial foods, or to track shifting seal populations. Most evidence so far suggests that land-based foods, like berries, carcasses, or goose eggs, cannot replace the high-fat seal diet needed to maintain large body size and reproduction at population scales. It is like asking a Formula One car to switch from high-octane fuel to lawn clippings. It might move, but not in the way it was built to. Perhaps one of the biggest mistakes people make about polar bears is thinking of them as symbols instead of systems. We see a single white shape on a small ice floe and read it as a poster for climate change. But behind that image is a precise machine shaped by hundreds of thousands of years of sea ice living. Hollow-looking hair that is not hollow in the way early myths claimed, but still brilliantly structured to trap heat. Skin so dark it drinks sunlight. Paws that read snow like fingers read braille. A nose that maps invisible plumes of scent across an empty horizon. A metabolism that can slam from feast to near famine without breaking. None of these traits are random. All of them are answers to a question the Arctic asked for millennia. How do you live, hunt, and raise young on a moving sheet of frozen ocean? Now, in barely a human lifetime, we have changed that question. The Arctic is warming about 2 to 4 times faster than the global average, a phenomenon known as Arctic amplification, documented by multiple independent analyses from NASA, the European Space Agency, and peer-reviewed studies in journals like Nature and Geophysical Research Letters. The ice forms later, breaks up earlier, and grows thinner. We have taken the stage polar bears were built for and are quietly rearranging it under their paws. So here is the deeper misunderstanding. Polar bears are not magically tough superheroes that will simply adapt to anything. Nor are they fragile glass sculptures doomed the moment a graph ticks upward. They are specialists, and specialists live on edges. We can measure those edges now, in shrinking ice seasons, in body weights and cub survival, in the chemistry of their blood and the fat in their tissues. We can see, in data from satellites and from researchers on the ice, how close some populations are swimming to the line where one more missed hunting season means collapse. The real question is not whether polar bears are built to survive. They are. The question is whether the world they were built for will survive long enough for them to keep doing what they do best. And that leads to one final question that only we can answer. In a melting world, will the most perfectly adapted animal of the Arctic be forced to change faster than biology allows? Or will we change the story of the ice in time for that white shape on the horizon to remain more than just a memory?